Hi everybody, in this video I'm going to talk about function transformations using vertical stretching and shrinking of graphs of functions. In other words, vertical scaling of functions. To understand what that means, let's take a look at our first example here, which says given y equal to f of x, draw y equal to twice f of x. So, we have this graph here of some arbitrary function y equal to f of x, and using this we have to draw the graph of y equal to twice f of x. In other words, we have to transform f of x into twice f of x. So, to understand what is going to happen here, once again we will use the machine interpretation of functions. We will think of this function f here as a machine f that takes some input and produces some output. So, let us say that for some input x naught, this machine produces the output y naught, and therefore, we have this input output pair x naught comma y naught. Now, what do you think this input output pair will transform to for this new function twice f of x? So, imagine this machine twice f of x, which I am just writing as 2f, and if I now plug in the same input x naught into this machine, what do you think is the output going to be? Well, because f acts on x naught to produce y naught, then twice f, what will that produce? So, first f will act on x naught to produce y naught, and then we have this 2 here. So, I should get twice y naught as my output. So, the input output pair x naught y naught should transform to the input output pair x naught comma 2 y naught. Very straightforward. But what does that mean in terms of the graph? So, let us take any point on the graph. Let us take this point here, which is x naught comma y naught, let us say. What will this point transform to? So, its y coordinate will double. Y naught will become 2 y naught, and therefore, this height here will double, and the new point will be, let us say, somewhere over here. And this is going to happen for every point on the graph. So, for example, if you look at this point here, this has a height of 1. So, the transformed point corresponding to this point will have a height of 2. So, the transformed point will be over here, and the points on the negative side of the x axis, their y coordinates will become more negative. So, if you take this point here, which has a y coordinate of -1, its new y coordinate or the transformed y coordinate will be -2. So, we will have this point over here and so on. But if you look at this point, which has a y coordinate of 0, the new y coordinate, the transformed y coordinate will also be 0, because twice y naught will be 0. So, what I should really get is something like a stretched version of this same function. I should get something like, if you can visualize this, something like this. And what I have done here is I have actually plotted it for you very accurately using a graphing tool. So, you can see this y equal to f of x, the original function, and this dotted function in the blue color is y equal to twice f of x. So, this point here stays where it is, but everywhere else you can visualize a stretching that has happened or a scaling that has happened to the original function. So, every point on the function, on the original function, the y coordinate of that point has doubled to give us the transformed point. So, that is what is really going on here in terms of transforming f of x to twice f of x, a vertical scaling, a vertical stretching by a factor of 2. Now, what if instead we have to transform y equal to f of x to y equal to 1/3 f of x. So, in this case, the multiplier that we are applying is not greater than 1, but less than 1. So, what do you think is going to happen here? Once again, if the original function produces for some input x naught, let us say the output y naught, then this new function, which is 1/3 f, what will this do? So, for the same input x naught, it will now produce an output of y naught by 3. So, the input output pair x naught y naught, the original one, will transform to the new input output pair x naught comma y naught by 3. So, in graphical terms, what that means is that every point's y coordinate will transform to 1/3 its original value. So, let us take this point over here. This point has a y coordinate of 3. So, the corresponding transformed point on the new graph will have a y coordinate of 1. So, the corresponding point on the new graph will be somewhere over here. So, there is a scaling down by a factor of 3. Similarly, if you take this point over here, which has a y coordinate of -3, the transform point will have a y coordinate of -1, -3 by 3. So, in this case, there will be a scaling in this way, in this direction, and the new point corresponding to this point will be somewhere over here. So, here you can imagine the reverse effect happening versus the previous case. In this case, there is not a stretching, but there is a shrinking of the original graph, and the zeros will stay where they are, because if the original height is 0 of a certain point, the new height will also be 0, but everywhere else the y coordinate will become 1/3 its original value. So, what we should get is something like this, and let us actually see a more accurate version of this plot in this figure here, which I have plotted for you. The original function y equal to f of x is this white curve, and our transform function 1/3 f of x is this dotted curve over here. And you can see that every point has transformed to a new point which has a y coordinate 1/3 of its original value. So, the whole thing, the whole original graph has vertical shrinking of the original graph by a factor of 3. So, let us summarize what we have learned so far. If you have to transform y equal to f of x to y equal to c times f of x, where c is some constant that is greater than 1, then what do? You take the original graph and you vertically stretch it using a factor of c. So, for example, if c is 2, then you take the original graph and vertically stretch it by a factor of 2. If it is 3, you vertically stretch it by a factor of 3, and so on. And the reason that happens is because any original point or a point on the original graph, let us say x naught y naught, gets transformed to the new point x naught comma c y naught, and c is greater than 1. So, any point above the x axis gets transformed to a new point that has an even larger height. It has a y coordinate that is even more positive, and any point that is below the x axis will now get transformed to a new point that is even more below the x axis, because the y coordinate will become even more negative. And therefore, you see this vertical stretching that happens if you multiply the function with a constant that is greater than 1. The important thing to note is that the zeros stay where they are. So, if you look at the original graph, the curve in white, these points are the zeros of the original function, and you can see that even for the new function, those are still the zeros, and that really helps us in plotting the new function, because we know that the zeros will stay where they are, and that is actually fairly obvious, because if you multiply, if y naught is 0, then c times y naught will also be 0, and therefore, the zeros will stay where they are. So, that is the case for multiplying with a constant greater than 1, and similarly, if you have to transform f of x to c f of x where c is less than 1, then what do? You take the original function or the original graph and vertically shrink it using a factor of c. So, if c is, let us say, half, then your new graph, your new function will be the original function scaled by a factor of half. And the reason that happens is that any point x naught comma y naught on the original graph will transform to the new point x naught comma half y naught on the new graph. So, the y coordinate is actually halving. If the original y coordinate is positive and lies above the x axis, then the new y coordinate will be closer to the x axis. So, it will come down in height. And similarly, if the original y coordinate is negative, then the new y coordinate will be less negative. So, it will come upward towards the x axis, and therefore, you will have this shrinking effect. A vertical shrinking will happen using a factor of c. So, that is the case for c less than 1. Now, to help you visualize this whole dynamic of multiplying a function by a constant, let me show you a simulation. So, here is a simulation in which I have some function plotted here, and what I can do is plot c1 times f of x, so some constant times this function and some other constant times this function, and I can actually vary the two constants. One of the constants I can vary in a way that it's greater than 1, and one of the constants I can vary in a way that it's less than 1. So let's first look at the case where the constant I'm multiplying is greater than 1. So right now it is exactly equal to 1, and therefore my plotted function c1 times f of x is exactly the same as the original function. Let me increase this constant. So look at what my new function c1 times f of x looks like. So as I increase the constant, you can see that the original function is getting vertically stretched more and more. So right now c1 is at 4.4. So the new function c1 times f of x is a scaled version of the original function, and the scaling factor is 4.4. So that's the case of multiplying with a constant greater than 1. And now let's look at multiplying with a constant less than 1. So what should we see? We should see a vertical shrinking of the original graph. So let's take a look. Now I am decreasing the constant from 1, I am decreasing it towards 0, and you can see that there's a shrinking happening of the original function, a vertical shrinking of the original function, because the y coordinates are all decreasing in their magnitudes. All right, so that's the behavior of a function when multiplied with a constant. Now let's quickly do a couple of questions based on what we have learned. So this first question says the graph of this function y equal to sine of x is shown below. Draw the graph of y equal to 3 sine x and y equal to minus half sine x. So what do you think should happen here in 3 sine x? Well, the original graph should just vertically stretch or be stretched by a factor of 3. And in this case, minus half sine x, what should happen? Well, you could do it in two ways. You could first flip this graph to make it minus sine x and then apply the scaling factor of half, which would be a vertical shrinking. Or you could first shrink this graph by a scaling factor of half and then flip it. So first we'll do the graph of y equal to 3 sine x. So that is a vertical stretching by a factor of 3. So how do we do that quickly? Well, we can start with the zeros. The zeros will stay where they are, because for the zeros, the y coordinate is 0 and the new y coordinate will also be 0. So the zeros will stay exactly where they are. So you can first fix the zeros, and your new curve will also pass through these points. And then what you can do is take some other points and then plot the transformed points. So for example, if you take this point on the original graph, this has a y coordinate of 1. So the transformed point will have a y coordinate of 3. And then if you take this point here, it has a y coordinate of minus 1. So the transformed point will have a y coordinate of minus 3. And then you can do it for this point here, which will give you a point here. And then for this point, you can plot the transformed point over here. So now you have a few points to work with to guide your drawing, and then you can draw the same shape but through these points. So let's do that. So I should get a curve that looks something like this. So it's a crude drawing, but it I think is fairly accurate in terms of what's happening here, a vertical stretching by a factor of 3. Now what about minus half sine x? So first let's apply a scaling factor of half, and that would be a vertical shrinking. But once again, let me keep my zeros the same. So I'll plot my new curve through these points, but I'll apply a shrinking factor of half. So this point here, which has a y coordinate of 1, now the new point will have a y coordinate of half. This one here, minus 1, the new coordinate, y coordinate will be minus half. So I should get a function of this, or a graph of this kind, and you can see that it's a vertically, there's been a vertical shrinking that has happened. So this thing right now is the graph of half sine x, but we need minus half sine x. So now what we'll do is simply reflect this graph about the x-axis. We've already learned that transformation, so we'll just do that, and therefore what we'll get is something like this. Okay, so that's the graph of y equal to minus half sine x. Now let's take a look at this second question. It says the graph of y equal to root x is shown here. We have to draw the graph of y equal to 1 minus twice of root minus x. So, this one looks a bit complicated, but once again we can do it step by step. So, first what we will do is from root of x we will plot minus root of minus x. And what should this be? We have already seen this elsewhere. We are replacing x with minus x. So, this should be a reflection about the y axis. So, this graph should reflect about the y axis to give us the graph of y equal to root of minus x. So, let us do that, and once again to help me do an accurate plot, I can just plot a few points. So, this point stays here, but this one comes over here, and then let us take this point which is 4 comma 2 comes over minus 4 2, and then I can see that there is a point 9 comma 3. I am looking for integer points because those are easy to plot. So, 9 comma 3 comes over to minus 9 comma 3, and now I have a few points to help me do a good plot, do a nice smooth accurate plot. So, that is the plot of root of minus x, but then I need 2 root of minus x. So, let me now change this to transform this to 2 root of minus x. So, what will we do? We will vertically stretch it by a factor of 2. So, let us do that. So, the 0 stays here, this point comes over here, this point y coordinate of 2 moves to 4, this point y coordinate of 3 moves to 6. So, now I can do my plot like this, and you can see that there has been a vertical stretching by a factor of 2. But now I need a minus here. So, this I will now change to minus 2 times root of minus x. So, what do I do now? I reflect this yellow curve about the x axis this time. So, let us do that. So, I will just reflect some of these points. So, this point stays here, this point comes over here, and then this point which is minus 4 4 comes over to minus 4 minus 4, and then minus 9 comma 6 comes over to minus 9 comma minus 6 over here, okay. And then I do this plot and I get minus 2 times root of minus x, and then finally I need this 1 here. So, I will just add a 1. So, now I will change this to 1 minus, or transform this to 1 minus 2 root minus x. So, I am adding a 1, which means that that is a vertical shift upward by 1 unit. So, I will just now vertically shift this curve here upward by 1 unit. So, once again I will shift a few points. So, this thing over here, this thing over here, and then this point over here, and then this point over here. So, I am just shifting a few points up by 1, and that helps me do my plot in a fairly accurate manner, and that is the graph that we need. So, that is all about vertical stretching and shrinking. I hope you understood the concept. I hope you liked it. Let me know what you think in the comments.